So in a square wave oscillator, what we do is we take a huge gain, let's say 500,000 times bigger. And if we put a very small signal in, what happens is that the output flies off to the positive and negative rails because of the huge gain. And if I take that and I feed it back through an RC network into the input, then I can disconnect this signal and the output will create its own input. But because of the large gain, what I'll get is a square wave out. Now to generate sine waves, what you need to do is you need to take that gain down to a more reasonable value so that the gain around the loop is 1. Let me just show you that. So let's say I've got a amplifier here which has a positive gain AV equals 10 times. So if I put in a little sine wave into this thing, which is maybe 0.1 volt peak value, if I put that into here, so I'll have a switch here that directs that input into this amplifier, and this will be times 10 positive output. So I put a little 0.1 volt signal there, it'll get amplified 10 times, and what comes out of here is a larger sine wave with a 1 volt peak. If I tap that off on a feedback path here, and I reduce that down to 1/10, let's say with a 9K and a 1K, then this point will also be 0.1 volts peak and in phase with what came out, which is in phase with what came in. So I will have, at this point, I will have 0.1 volt peak to peak with that phase, and at this point I have 0.1 volts peak to peak with the same phase. So what I can do very quickly, if I flick this switch over to here, now what I've got is I've got the 1 volt peak getting reduced down to 0.1 volts peak, and then it goes in and feeds itself, gets multiplied 10 times, and gets me back my 1 volt peak. So I've created an output that turns around and feeds itself. Now, in order for this to work, you need 2 conditions. So number 1, the gain around the loop must be equal to 1. So the AV loop must be equal to 1. If the loop gain is too big, then what tends to happen is that the output gets bigger and bigger and bigger and bigger until finally you hit the positive and negative rails and you end up with a square wave. If the loop gain is too small, then what will happen is the output will get smaller and smaller and smaller until the oscillation dies out. But if you have a loop gain of exactly 1, then you will get a continuously running oscillation that feeds itself. So now the other condition that needs to be met is that the phase shift around the loop must be equal to 0 degrees. So that what is coming out here has to get fed back into the circuit with the correct phase in order to create what is coming out. So you need 2 things. You need a loop gain of 1 and you need a phase shift of 0. And if you can satisfy these 2 conditions, you will get a continuously running sine wave oscillator. Let's take a look at a couple examples. So here's the phase shift oscillator in Multisim. You can see the 3 RC networks, and each one of these is supposed to shift the input by 60 degrees and reduce it a little bit. So I apply a signal here, Vn0, and we would say that this one is at 0 degrees, and then 1 would be shifted 60 degrees, 2 would be shifted 120 degrees, and 0.3 here would be shifted 180 degrees. And it should be about 1/29th the amplitude of what we originally started with. So appearing at the input of this non-inverting amplifier, it's 180 degrees out of phase and 1/29th amplitude. So this non-inverting amplifier, we want to kick that up 29 times. So what we have coming out is the same peak as what we started with, but it's out of phase. And then we're going to put it back in phase with this inverting amplifier, so with a -1 gain. And so coming out of here, Vn5 should be the same amplitude in the same phase of what was originally coming in. And so now we've got the phase shift oscillator. The output is feeding itself, and there's only one frequency that's going to get through this RC network and appear here in the right phase that will get amplified and create this loop. So our loop gain needs to be 1 and our phase shift needs to be 0. So last note here, I'm using a non-inverting amplifier here because if I use an inverting amplifier, I'd have to deal with the Z-in of the 1K or so, and that would load this circuit down and change its frequency of oscillation. So I'm using a non-inverting amplifier to get myself a high Z-in. Now I have connected these points to various measuring equipment. So here's a 4-channel scope where I can look at VN0 to VN3. Then there's a 2-channel scope, and with this one I can compare what's coming out to what went in originally. And then this one here, a Bode plot analyzer, I'm going to use that to look at the phase shift across VN0 to VN3 and figure out what frequency is getting through with the right phase. So let's start the simulation. We'll press go here. And the first thing I want to look at is I want to look at the 4 points along the input filter. So what I'm going to do is I'm going to drive that with a function generator, a known fixed value, so I can make sure that I'm getting the right reduction and the right phase shift at each point. And that's shown here on the 4-channel scope. So I'll pop that up, take a look, put it on normal, and then we'll freeze it. So if I go along here, you can see the biggest waveform here. That's obviously VN0, that's the one that's coming in. And then the next one down, there's a little bit of an attenuation from the resistor capacitor network. So VN1 is going to be a little bit less. So that's going to be this peak here. And you can see that it's down quite a bit and it's shifted quite a bit. VN2 then must be this one here. I'll move this over to VN2. And it's shifted another 60 degrees and it's down again. And then finally this little hump right here, the smallest sine wave, that would be VN3. And it looks like that one is 180 degrees out of phase. So here you can see the input is going to its most negative value, and this small waveform is reaching its peak positive value. So it's about 180 degrees out of phase, and we could figure out what the attenuation is by comparing the voltages. But it should be about 1/29th. So the next thing I want to look at is with this scope here, I want to compare VN0 to VN5, and I'm going to feed it with the generator. And what we want to see is as it goes through this network, it comes out here on the output and it comes back in, and this voltage needs to be the same magnitude and the same phase as the generator. And then I'll be able to flick this switch over to here and we'll get the circuit to drive itself. So I'm going to pop this up here, and here you can see we got 2 sine waves. So one of them is the final output here, and the other one is the function generator. So one is the output here, and one is the function generator. And you can see that if I play with the gain a little bit, so here's the gain potentiometer. Right now it's at its maximum, and the output is a little bit bigger than we need. And if I tweak it down a little bit here, I'm going to reduce it. You can see I can also make it a little bit less than what we need. So I use this pot to adjust the gain to get a loop gain of 1. And when the gain is 1 and the phase is 0 degrees, it should oscillate on its own. So I'm going to set this to 1. Maybe a little tiny little bit more. And then I'm going to flick this over, and we're going to see if it oscillates on its own. So I flick that over, and you can see that it went up a little bit, and it continues to oscillate now on its own. It's been disconnected from the function generator, and it's driving itself. Now, if I play with the gain pot here, if I go up, up, up with the gain pot, you can see what happens is that I'm overdriving it, and it starts to distort, and we get some flat spots on the peaks. So if you have too much gain, the signal increases until you see flat spots. If I don't have enough gain, we'll tweak this down. You You can see I don't have enough gain now, and it's slowly dissipating away as through every loop. Like the first time through, it's 0.99, and then it's 0.98, and then it's 0.97. So it's slowly decreasing in magnitude until the oscillation will die out. Now, if I go back up again, you can see now it's increasing until the oscillation reaches its peaks. So this gain factor and trying to get it 1, it's a little tricky sometimes to get that perfect. But if you play with this a little bit, you can adjust it until it sits at a nice constant value. The last thing I want to demonstrate here is that sometimes when you start the simulation and look at the scope, it looks like the oscillation won't start. Now, what makes the oscillation start is generally some thermal noise or some random variations in the circuit. And once it gets going, once something moves in one direction, then the oscillation will start to go on its own. So right now I see nothing. I'm going to come over here and I'm just going to hit this switch really quick and toggle it over here to the generator. And then you can see the oscillation is off and running, and it's slowly increasing until we get full amplitude. So there you go. So a little bit of random noise will get the oscillation going. So to do that, you might need a gain that's like 1.01 just to make sure that it gets up